we come back for the next following session.
4 o'clock is fine.
Thank you.
Bryan Nelson is a ceramic engineer from Missouri Science and Technology back in 1977-1981. He has 19 years of working experience for North American Refractories Company, doing research, technical services, and marketing in the non-ferrous metals market. Well, 3 years of working experience for National Refractories, heading up for the non-ferrous metals group. 9 years of working experience in sales for Spire INC. Since 2012, he has been working with Allied Mineral Products in sales and is now technical manager non-ferrous metals. He is an inventor of porous plug technology for injecting various gases in aluminium and copper. As I told you before, the topic is advanced aluminum refractory technology for the 21st century. It's my pleasure and it's our pleasure to have you, Bryan, for this session. Welcome, and you're good to go. Can you hear me, Nelson?
I can, thank you.
Yeah, please go ahead.
Okay. There. Yes, good afternoon, everyone in India. It's a very early morning here in the United States, and I appreciate the opportunity from ALUCAST to make a presentation on an area that I have been had the pleasure of working in for the last 40 years. And I guess I have a kind of a unique perspective because I have 20 years of working for refractories for aluminum in the 20th century and now 20 years in the 21st century. So I guess right now I'm balanced between the old and the new. But I think before we can go too far into the 21st century, I think it's always good to know where we came from. And again, because of my advanced age, I can speak to where we came from firsthand experience. So basically, when I started in the 70s, aluminum furnaces were lined with high-fired Super Duty brick. That was primarily brick furnaces back then. When I started my career, 80% of aluminum furnaces, or just any type of refractory container, dropping every year. And mainly this is because of expense, lead time. It's getting harder, I'm sure, around the world. It's definitely here in the United States and Canada to find skilled brick layers anymore, and that are able to lay brick with very tight brick joints, because as we all know, aluminum has the viscosity of water. So any kind of a joint is going to penetrate. So again, when I started, because of the temperature of aluminum between 750 and 815 C, a Super Duty brick with around 45% alumina, 53% silica was quite sufficient. But the problem is this reaction here. With the aluminum in contact with a silica-bearing refractory, if you look at an Ellingham plot, for all those engineers that remember their thermodynamics, that it will reduce the silica to silicon and alumina, which we call corundum. Now, what's interesting about alumina is we manufacture refractories with alumina. It's just a different crystal structure. The alpha alumina that we use is not as hard as corundum, which the corundum crystal, as I think most people might know, is after diamond is one of the second hardest materials on our planet. So as I affectionately call it, the corundum, as you can see in this photo right here, is a furnace killer. You can see even as it grows in this corner, you start to see a separation between the lower sidewall and the upper sidewall. You can see it's starting to crack the existing refractory. It's very expansive when it goes from molten aluminum to corundum. There's a very, very large volume expansion. Again, destroying the refractory containment vessel. So what historically, what the aluminum manufacturers had to do is they put in the high fired super duty, and it was high fired because it lowered the porosity. But what they got is what they call silicon bleeding into the aluminum through the reduction reaction. You can see here with the high fired super duty that based upon the thermal profile through the refractory lining, it followed that thermal profile as far back as it could maintain liquid aluminum to reduce the silica in the refractory. It dumped high percentages of silicon. And I guess, as long as you were making die-cast alloys, not so bad. But if you're making 5,000 series, 3,000 series, 7,000 series, high silicon was very bad for the alloy. So what did the industry do? Well, we migrated to less silica. So we jumped, even though you don't need it because of the low melting point of aluminum, but we needed something with lower silica. So we went to an 85% Phos bonded bricks. And we dropped from 53% silica to 11, effectively reducing the amount of silica that can be reduced. And the phosphoric acid that was used to make the bricks, again, lowered the porosity, less surface area because you have less pores for it to penetrate, less open porosity for the aluminum to travel into. So this was this migration happened and worked all the way through the 80s and late 70s. And around that same time, because again, you don't need 85% aluminum for a use limit, and the industry wanting to do monolithics, castables, because conventional castables were with higher than 2.5% calcia, had been around for probably 20, 30 years. Now they wanted to use that in the metal contact. The monolithics had been used in the roofs. Conventional 60% aluminum had been used for a couple decades. But once scientists in my industry were able to find non-wetting agents that you could add to the refractory, that was a major milestone in the refractories industries for aluminum. So again, about a 65% alumina. This is an alumina salt flux test, which is a test that my colleagues and I in research in the 80s developed, and it's used to this day, where you can change the various type of aluminum alloys, and you use salt flux because again, the aluminum producers use covering fluxes to minimize metal loss through oxidation. They have wall cleaning fluxes. There's all kinds of different fluxes that are alkali based and fluoride based, which have a deleterious effect on the refractory. So we want to test for this in order to make improvements. So for many years, again, it was in the 70s, there was again the 65% alumina. Even though it had 30% silica, the non-wetting agents are very powerful for reducing that or minimizing the reduction of silica. So Again, in the 80s, they would already be using an 85% aluminum brick. So we developed an 85% aluminum monolithic, again, trying to minimize the silica content from 30% down to 8.5%. And then in the 90s, we developed in our industry Phos bonded castables and eliminated the low cement castable, the cement, the calcium aluminum cement bonding that held all the particles together and gave it strength. It gives the refractory excellent strength, but it also adds brittleness to the refractory. It's not quite as thermal shock resistant. There's dehydration of the cement in a castable. There's 3 or 4 critical dehydration points that you have to be sensitive to during the dryout. So your dryouts period are longer, which means handing it back to production for a reline or repair takes longer. So the industry was wanting, again, materials that you could do things like extend the life of the furnace. And in the destruction of an aluminum furnace, you have things as, mechanical abuse in the jambs, lintel, and sill. You have the corundum and its ability to destroy the refractory, as you saw in the first pictures on the first slide. And in order to improve the furnace life, we needed to develop better repair materials. So you didn't always have to tear out all the refractory back to the shell and build it back with new materials. Was there a way that we could just clean any penetrated material away and then build back the thickness of the walls and floors without having to tear everything out? This would save a lot of money and a lot of time. The industry demanded, again, faster installation and dryout, and without any minimizing the disastrous effects on the furnace life. In order to do this, you needed more formless. Forming became an issue in the amount of time it took to reline. So the industry was saying, hey, can you make something that can be sprayed on? And the next thing they wanted is a faster dryouts, again, to turn it back over to production even faster. So they wanted things in the 38 degrees C per hour or higher, where historically it was more like 16 degrees C per hour, and they wanted to go to 38 degrees C. And they wanted things that are safer. There was, issues with silicosis that you have to deal with. There's also the 2-component phosphate bonded castables. The liquid additive was phosphoric acid, which requires special PPE, air quality monitoring, things like that. So these are some of the things that were driving us from the 20th into the 21st century. Again, the 2-component phos bonded castables, where again you have the dry material and the liquid phosphoric acid, was a monumental improvement in refractory life in aluminum furnaces and all containment vessels, dosing furnaces, launders. All of these life was dramatically improved. Easier cleaning when we went to the liquid phosphoric acid systems. I have done extensive over the last 40 years. I've tested literally hundreds of refractories from around the world in contact with various aluminum alloys and salt fluxes. And I have found that the phosphoric bonded materials has resisted every alloy that I have tested it against. It's, again, an outstanding technology. Again, it has the added benefit of bonding strength. Again, as I mentioned earlier, the industry was demanding repairs as opposed to complete relines. So we had to find something that would, bond and adhere to the old refractory once we cleaned it. And can we do it? We ended up doing veneer casting and gunning. We have both technologies to allow you to repair. We've achieved the rapid dry out of 38 degrees C per hour or even higher. And the other added benefit of the Phos bonded castable is superior thermal shock resistance. It's tremendous. And later on in my presentation, I'll show you spalling test to show you how effective it is. Here you see typical cobblestoning in an aluminum furnace wall. Like I always tell everyone in my presentations, in my 40 years, if I get a call from a customer with a complaint, it's almost never about the lining wearing out prematurely. They didn't get the life that they expected due to wearing of the lining. Almost all the calls I've ever received have been about cracking. They've looked in the furnace and it's all cracked. Pieces are falling out. Maybe there's a large crack after dry out, things like this. So what I really love about this product, again, as you can see in the picture on the right, where there's a 91 metric ton reverb melter after 7 months of service. I apologize that the picture wasn't zoomed in a little closer, but I think you can see even from that distance, you see the vertical cold joint that the contractor put in, but there's none of this, none of the cobblestoning, because it takes the thermal shock so much better than a cement bonded castable. This is again showing what you normally see at the belly band area here, the interface between the lower sidewall and the upper sidewall. Again, the corundum has penetrated, and in the cleaning of this wall, you get a deep depression. You can see the corundum. They haven't cleaned it all out yet. This again is very typical of corundum, that it wedges itself in corners. And again, when they knock that off, you're going to get a depression in the wall again. This particular customer went back in with the 2-component phosphoric bonded castable, and you can see from the difference in the emissivity differences between the old and the new, you can see where they installed it. And again, after 3 months, the improvement in resistance to adherence of corundum and aluminum is fantastic. You can see how clean those areas that have been repaired. As I mentioned earlier, to give the industry what they wanted on repairing old refractory, we have done 2 different types of repairs: a veneer casting, where you actually place a form, a wooden form, and after you've cleaned this with a hydraulic hammer, then you just pour back to get to your original thickness. And you can see here in the middle picture here, that wall after that was veneer poured back. And then you can see just again how cracked the upper sidewalls are. These are very typical pictures. I'm sure all of you that have worked in an aluminum foundry have seen this many times. And what we have done with this furnace is we've veneer cast the lower sidewalls, and then we gunned the phosphoric acid in the upper side wall to repair around the burner ports and bringing the wall back to its original thickness. And what we're seeing with this is, if to get the furnace to this condition here, it took, say, three to 4 years, and they've lost this much. When they veneer cast, we have found that you can add another 3 years of life. It was interesting. We worked with Alcoa. They had been using a colloidal silica gun mix to repair furnaces to keep them going, and we wanted them to use the phosphoric bonded materials, and so they gave us the challenge that you had to get 3 years life in order to justify the price difference between colloidal silica bonded refractory and phosphoric bonded refractories, because they are significantly more expensive than either cement or colloidal silica bonded refractories. And I'm happy to report that we accepted the challenge and we met the challenge. We did receive 3 years life extension by veneer casting. But as you're always up against production and they're wanting the furnaces back quickly. So the customer is, they still veneer cast from time to time, but they really have gone to just gunning our phosphoric bonded materials. And that will add about 18 months extension of life. It's not as good as veneer casting, because there you're vibrating versus gunning. But the colloidal silica would last about 9 months to a year. The phosphoric bonded gun mix would last 18 months, and veneer 3 years. I've given you, I think, a very good indication of the upside, the positives of the phosphoric bonded 2-component refractory. The downside is it is considered a hazardous material. I don't know about India, but I know in China, as well as here in the United States, it has to be shipped in a hazardous chemical truck. So it's shipped separately from the dry material, which adds an extra cost of transportation. And again, I mentioned about the PPE, because again, it's an acid. So the contractors that put this materials in have asked, can we make this type of product, but use water to make it into a concrete type consistency, something that you can pour or spray, but it's activated with water as opposed to phosphoric acid. So that it was not an easy challenge, but I'm happy to report that in the 21st century here, we have answered that challenge and have developed a single component water activated Phos bonded castable and gun mix. To meet that challenge, we did not want to lose any of the benefits of the phosphoric system of the 2-component. So we started running tests. This is just a aluminum cup test without the salt flux and with 7075 alloy. And you can see that we run the test at 815 degrees C because, again, in my experience, and looking at oxidation graphs of aluminum at 815 degrees C, the oxidation is astronomical. I mean, it goes up from liquid to an oxide. It's the slope of the curve is vertical. So that's why we run the test at this high temperature. We would hope that you would not run your metal temperature that high. but to have a very rugged test, we run at this temperature. And you can see using the liquid or using water with a dry component of Phos, we were able to maintain the refractory's ability to totally resist aluminum reaction and reducing of the silica in this refractory. I promised you we talk about the spalling. This is an extremely rugged test. The industry asked for 38 degrees C per hour ramp rates for dryouts. For the explosive spalling test, we ran it at 16 degrees C per minute ramp rates to 815 C. This is an excellent low cement 84% aluminum non-wetting castable that we have put in all over the world. Works fantastic. But as you can see, because of, again, the dehydration points of aluminum that of a castable, it will explosively spall. It will come apart. The two component, again, it took the extremely rapid heating rate with no spalling, and we're happy to report that the single component Phos bonded castable also did not have any explosive spalling. The next criteria was the bonding strength. The added benefit when in the 90s, when the Phos bonded two component castables were developed, they had that ability to bond like super glue to existing refractory. And so we wanted to make sure we didn't lose that. And again, we're happy to report that when we do when we cast the single component material to a brick and break it in a MOR 3-point bend test to measure the tensile strength of that joint, the single component was just as strong. Probably statistically, there's probably not much difference between those two numbers, but it definitely was not less bonding strength. So it's nice to do things in the lab to come up with things, but always the proof of any product is how does it work in the field. And on the left is an aluminum furnace that had the low cement type castable. This furnace ran for 5 years, so it did an excellent job. But again, we were always into a continuous improvement mode. So that furnace, when it was relined, was done with a single component castable. And again, you can see here, after many months of operation, you do not see buildup in the furnace at all with a single component. Now, moving to the second product that's been developed for the 21st century is products that are based on the high levels of calcium oxide. And why did we go from using Alumina-Silica based materials to materials that are Alumina-Calcia based? Well, the reason, again, as I started off the presentations with showing how aluminum metal reduces silica. And the industry for the last 20 years have been making refractories with lower and lower levels of silica. Well, how about eliminating it totally and putting in a material that, from a Gibbs free energy standpoint, cannot be reduced at all. You can see here with a calcium oxide plus aluminum will give 2 calcia plus 2/3 alumina, but the Gibbs free energy is positive, and only a negative Gibbs free energy would allow for the reaction to go from left to right. So if if it's positive, this cannot happen at 700 degrees C. So that's why we developed the refractories with calcium. On the left here, again, is we ran the aluminum salt flux test. And what you're seeing here, this is not aluminum. The aluminum slug, that the molten aluminum, when it's solidified in this cup, was able to be withdrawn from the cup just with their fingers, pulling it out. No sticking at all. This is only the solidified salt flux that's left in the cup. And as you can see in the interface, zero reaction. And again, this test is done at 1,000 degrees C, which is extremely high temperature. And even you can see that, again, the calcia is not reduced. There's no silica to be reduced, and subsequently, you have a refractory that is not attacked by molten aluminum. And again, here you can see the peelability. This had aluminum up to this level, and we were able to pull the skin of aluminum out of the refractory without any coatings. Because again, the industry, to have a parting plane historically has used coatings, but this just with itself, with no coating, it peeled perfectly.
Hi, Brian, sorry to interrupt you. It's been really interesting, but if you can wrap it up in 3-4 minutes, that'll be great. We're running against time.
Sure.
Is that okay? Yeah, thank you.
Yes, I can do that. Okay, the other advantage of this calcia-based is the thermal conductivity. You can see here with these are two calcia-based, these are more typical refractories, and you can see that it's less than half of the conductivity. So with that difference in conductivity will translate into lower temperatures of your shell. With the calcium-based materials, you have 139 degrees C versus 191. So I know in a lot of parts of the world, energy is a very large cost. So lower heat loss is a fuel savings. This is, Michael alluded to the dosing furnaces that was feeding his machines through the dies. And here's a dosing furnace using the calcium-based materials. These things are lasting 5 to 8 years. With, again, you can see almost zero penetration and very easy peelability. Same thing with a heated launder. Again, after 30 days, and historically, workers are terrible about cleaning the walls off of the aluminum, and this is easy to clean because it doesn't stick. And just to mention on the way out the door here of my presentation is that we are located in India and many other, we have 13 manufacturing plants all over the world. And we're very much in India, and wanted to mention that. We have 3 research centers as well, which more near and dear to my heart. And our local guy is Gulab Patel. And so if anyone would like to contact Gulab, he would love to talk to you. And see, Rahat, I finished with less than 3 minutes.
Yeah. Thank you so much. You were dot there. Thank you so much.
You thought I had another 10 slides.
Yeah. I thought the new product would come with another 10 slides. Yeah. But then thank you so much. It's been so interesting, to hear the things and the insight into this, this subject of refractories, and particularly this veneer casting, which you said about 3 years lifetime, is a really nice thing to hear. And I was listening about phosphoric bonded material, and then interestingly, you pointed out about liquid phos, which is hazardous material therein. Some of the countries don't accept it. So. And then in the end, you talked about thermal conductivity and energy. Well, you truly pointed out that energy is one of the is the key in India too. It's an important expense, in terms of so energy is a major constituent of the cost. So, I invite my colleagues and friends from the community to ask questions. We have a question from Mr. Sripad Kate, and he's asking that are these discussed refractory materials like double component Phos bonded castables available in India?
Yes.
Can you elaborate more on this? I mean, from yeah.
Yes, we have a manufacturing plant in India that again, we're making refractories for the aluminum industry. And if we don't have a particular product right there in India, we have 3 manufacturing plants in China so that we can bring down from China. But our intention is to make everything in India and transfer all of our technology. Allied's philosophy is to put our manufacturing plants where metals are being poured, whether it's aluminum or iron. That's where we want the plant. We want to minimize the logistics of shipping from other countries. And at least 3 years ago, I would say, we started up our India plant. So, and it's growing every year, every month. So yes, they are available. Everything is available in India.
That's super great because it's actually very important to have this in India, and with local logistics and availability, it really makes a difference to add value to the process. And I see that there are no more questions right now. There might be a few which will come up maybe in times to come. So, there's another. Okay, is that a question? We have the ability to produce a complete line of products in India. Okay.
No, it wasn't a question. I'm from Allied Mineral also. I was just chiming in that we have the ability to make the full line of products in India. And we do extensive testing of raw materials on a continuous basis so that we can ensure the quality of the raw materials. If we can't find the quality raw material, then we will import possible, certain parts of from other parts of the world, but we manufacture them in India. And I would say about 80% of our raw materials are local.
That's wonderful to know, actually. That's really nice. Great.
So
and
sorry about that.
So
I didn't mean to interrupt.
That's okay. That's okay. But thank you so much for this wonderful presentation. And it's time for the next session and the last session of today. And let me introduce about this session. Sumida, if you can just give that slide.
Sure.
Okay, great. So when it comes to pressure die-cast, good and high quality die-cast parts, the use of vacuum automatically comes in mind to many die-casters. So having a look closer into the vacuum pressure die-casting production, one of the key elements is which vacuum. Hello?
Hello, can you hear me?
Yeah. Yeah. So I was talking about, having a closer look into the vacuum pressure die casting production. One of the key elements is which vacuum level is needed to successfully produce a particular part. This paper presentation will give an overview on recommended vacuum achievement in the die cavity as a guideline with basic explanations. So let me introduce about the speaker. Mr. Jan Emmenegger is a mechanical engineer and has done a 2-year airplane engineering technician course. Very interesting. He also has a business management degree and a marketing degree. Presently, he is the director technical instructor with FONDAREX Engineering, working with the pressure die casting industry for 29 good years in many specified applications in the high quality field. Global experience in many points of view. So, friends, we have a very interesting presentation from FONDAREX, one of the leading companies for vacuum in the world. And I welcome Mr. John Emmenegger to have his presentation. We'll have 35 minutes of presentation from you, and then followed by 5 minutes of question and answers. Welcome, Mr. John.
Thank you very much. Can everybody hear me?
Yes, I suppose, yeah.
So let me see if I can put my presentation on. I don't know if I have to put it on the main screen or not. I have it right here. So I have to take this with the partage écran. So you can see me as well, or you just hear me? Hello?
Yeah, the presentation is yet to come. We can only see your name right now.
Yeah.
Yeah. You had to share a screen, yeah? Yeah, that's it. Yeah.
Yeah, I do. Yeah. So let me see now. It should be on. So yeah.
Yeah, there you go. We can see it.
Right.
So you can see full screen, yeah?
Yeah. We can see it, yeah.
Yeah. All right, so I can start. Thank you very much for having me. I think, well, I kind of feel proud. I think it's my 4th presentation I have in my career as a FONDAREX engineer at ALUCAST. So I had to find a little bit another task again, because it's always about vacuum. And so yeah, this year I'm proud to be part of ALUCAST, the first time online, yeah. Otherwise, I mean, of course, I love to come to India. This year, unfortunately, I couldn't do a trip, so we'll do it over the computer. Okay, so my presentation this year is a little bit about vacuum level and all around vacuum level and vacuum curves. Because everywhere we go, and sometimes on the phone or on email, people always ask me, oh, I got this product to produce. How much vacuum do I need for this? What should be the vacuum level? What kind of equipment? How should the application look like? And so on this presentation, we are more or less just talking about different vacuum levels and maybe some influences and of what we can do to the level and what kind of side effect it has. So I got some overview on it. So the vacuum level, what does it do to the metal structure? Then vacuum pressure die casting of what do you need? Then influences, side effects to the vacuum tank recommendations. And also one of the tasks, of course, is structural pressure die casting, sealing of dies, and so on. Yeah. So to start, of course, why do we have metallurgical problems in pressure die casting? As everybody knows, low pressure gravity casting in most times has better structures than aluminum pressure die casting. Mainly it is because of the fast filling, where it entraps some air and therefore microporosity shows off, and in many cases also larger porosity comes up. And then of course also through the fast cooling rate, we do also create some shrinkage porosity, micro shrinkage porosity. It's kind of a complex, happening during the solidification with everything we have entrapped into the alloys. So if I go a little bit further, the non-uniform properties tends to increase with thickness and size of pressure die casting components. And therefore, also, if we have thicker parts, the solidification even becomes more important. Therefore, also the vacuum is important, because once we have a perfect filling, the solidification is actually getting more precise, and therefore we also get better microporosity. The secondary alloys we are talking about, they do have some elements of intermetallic phases, and sometimes, of course, oxidation comes up, and also we can see water elements, H2 elements, which are included in the excessive hydrogen melt. The hydrogen, of course, mainly comes up in pressure die casting because most die releases are water-based, and therefore also we do have a little bit more H2O, which is getting mixed with the alloy structure. And there we come also to a positive point with the vacuum now before we even talk about the level, because the vacuum basically also is taking out part of the humidity. So this is happening already below 500 millibars. And of course, a good application, we'd like to get 200 millibars or even below in high quality pressure die casting with vacuum. And the question is always like, how much should we get? People talk about 100 millibar, about 50 millibar, and so on. Me, I have made many good castings by 400 millibar. Why? Because we didn't have the time to get good vacuum, or sometimes also what we will learn later, that if the vacuum is getting too good, the side effects of the vacuum are getting higher, and not everybody is able to manage them. So now if
I'm just interrupting you. There's a request. If you can switch on your camera, people would want to see you also.
To see me?
Yeah, there's a request here, please.
Yes, can you see me or not?
No, I think you switched on your you switched off your video. Maybe if you can switch on your
video
camera, the camera. Now you're there. Yeah, we want to see this handsome guy.
So I'm sorry for that. Yeah. So here we go.
That's okay.
Yeah, and so you can see the full screen, or you can see the part of screen.
No, the screen is also visible, and it's all okay.
Okay. Oh, perfect. So you can see the 200 millibars thick marked. Yeah. So okay. So now this is why, in compared to standard venting, vacuum venting will reduce automatically the air content inside the die and in the shot sleeve as well. So even if the vacuum level is not as good, we have already less vacuum. So if we look at the praxis, this is how it looks. Standard venting, which probably is 85% of all pressure die castings made in the whole world, are with overflows and some vents. For many parts, this is fine because the quality requirements are not that high. What happens in such an application? In the first phase, the aluminium is traveling with low speed towards the gate, and inside the cavity, the air is compressed. Let's say when the metal gets to the gate, somewhere between 1,200 and 2,000 millibar, all depending of the overflow and the ventings, which are built into the die. From where we can see from this picture here, where we can see until the end of filling, depending of the cavity, it is somewhere between 10 and 100 milliseconds. And therefore, depending of the application and depending of where the aluminum travels, it will go towards the overflow and you will compress the air inside the cavity. So in worst case, this can go up to 100 millibar, or let's say 100 bar at the very, very end of the filling, when air is entrapped into the alloy. So now this is why FONDAREX actually invented the vacuum venting. Was it like back in 52 or something? So that's like almost 70 years ago, where the first vacuum system has been invented. And the target is, once the alloy gets to the gate, that we have reduced the pressure inside the cavity to maybe 300, 200, 100 millibar. And in very best case, maybe down to 20 millibars. So the less air and the less gas, or let's say the less gas, air is a gas, but the less hydrogen from water we have inside the cavity, the better the filling is, and the less the alloy structure, the alloy particles get involved with the metal. So therefore, at the very end of filling, we may still face 250 millibars. So now, according to 4 or 1 or 10 bars, this is a very high difference. Going a little further, I will later on show you some curves on that. So in solidification phase, the 100 bars, in extremities, it can go up to 800 bars. So this will be a very, very small air bubble, which is compressed during the solidification indentation phase up to 800 bars. And then, of course, during the solidification, once the pressure doesn't reach there, this pressure goes back, and therefore we show a visible porosity. So this is how it looks in a tomograph. If we make a tomograph of a pressure die cast part, you can see without vacuum, we will find some microporosity in many different places. And even if we cast with vacuum, there will be still some small remainings left in some places. So this may be mixed between shrinkage and air and gas. Or if we do an X-ray, we can see some shrinkage, and we can see also a little shrinkage even with vacuum here, but it significantly gets better. So that means the structural integrity is a big failure point in basically all pressure die casting parts. The question is always, do you find it out? Is it after machining showing off? Are the parts pressure tight, or do they need to be pressure tight? Often the skin in the outside, as long as it's not after machined, is good enough that even some little porosity remaining inside the part is still accepted. The shrinkage porosity, of course, is mixed most of the time with the gas and with the air porosity, and somehow we have to find a good mix between vacuum, temperature, and sometimes even a squeeze pin, which will do a fantastic job together with the vacuum to create a good pressure die cast part. Now, looking at the structure to see what is the difference. Without vacuum, the pressure always increases. With vacuum, we try to get basically no air inside the cavity. Looking a little bit more precise on it, without vacuum, everything is controlled up into the filling phase. But then at the very end of the filling phase, we can see that the air, which is entrapped, and most of the time we cannot even bring all the air and gas out. It is somewhere entrapped into the alloy, and it will go up to 10, 20, up to 100 bars at the very end of the filling. And there is the big problem, that the last 10 milliseconds. In the last 10 milliseconds, a lot of things happen which we are not able to control if we do not work with vacuum. And this is a very positive point in vacuum, because we take out the air before the metal is at the gate. And once the metal is at the gate, we remain with a rather low pressure, or let's say almost no air, somewhere between 500 and maybe 20 millibar. 500 would be here, and 20 down here. Now, how good this vacuum curve is, it sometimes shows directly in the result, or rather we have to talk about which curve does not influence the metal flow as much and does not get additional air into the die. So that curve, if we talk about pressures, about how much pressure we have to create. There are many, many differences in the world of die casting. And it's not like the one pressure which we say 200 millibar is good for that part. We have to experience on one application. We have to make 100 shots, 200 shots. We have to X-ray the parts. We have to adapt the parameters. And maybe after 200 shots, we know 150 millibar with those kind of parameters are good for this application. And afterwards, we can trigger the parameters in the vacuum unit to say if we are out of tolerance, that means higher than 200 or maybe lower than 100, we are not in the field of like how the parameter or the all over parameters are set in the pressure die casting application. So this is a little bit how to start. We are not knowing on a paper or on a computer exactly how much vacuum we have to have. We have to work it out of how much vacuum the die gives and what kind of parameter we can set together with the die cast machine, with the mold, with the application we are having. So if we go a little bit further, vacuum has a lot of influences, and this is where the key point is. We have to handle all the influences who are creating those different curves. As we can see here, we have one curve which I put in orange, which I would consider is not a good curve. Why? Because we can see it comes quickly down and somehow we don't get any further. It's the proof of probably we have a big leak somewhere. We cannot get a better vacuum into a mold because there is too much leak. So we'd rather have a curve which comes down like this and still going down all the way until the filling phase is done. So we are looking at different influence points. So we have additional air being sucked into the cavity, often a big problem. Dilute, mainly water, being sucked into the cavity or already inside the cavity, and actually the volume which we have to take out of the die, the gas volume, will become much higher. Because if the water gets in touch with the hot mold or with molten metal, it's kind of like an explosion. It gets up to 200-300 times its volume. And all this water, H2O, or later on hydrogen, is a big problem inside the cavity. Then another big problem is air being sucked between plunger and shot sleeve. We have to start the vacuum somewhere after the plunger overtakes the pore hole, and often the plungers are not tight enough, and there's always some influence that some air comes in there as well. And then of course the turnover of oxygen is higher, and instead of like having better castings with vacuum, some people say, well, I tried to vacuum, but I didn't get any better parts. Why? Because we took out some air, but some other air came in, and at the very end, we had a higher turnover of oxygen, and the parts were not any better than without vacuum. And another big task is the alloy flow in the runner, from shot sleeve to runner, in the runner, sometimes even in the cavity, is getting slightly different under the use of vacuum. And therefore also we have to find a good way of like how much vacuum in which sector we need to have an optimum airflow inside. So to start with the side effects, it's always like how tight is the die? People ask, can I use an already existing die? Of course, an existing die can be used. We may have to overhaul it a little bit. We have to check that there is not much flash, or if there are sliding cores, that the sliders are fitting well into the die. And then even existing die, yes, we can still use. The problem is often, or maybe it was in recent years, often the dies, they were precise at at 20 degrees Celsius in the tool room. But for vacuum die casting, the die should be tight at 160 degrees. Or let's say the inside of the die is maybe 160. The frame, the die holder is maybe 70, 80 degrees, depending of the size and depending of the environment. So basically the die must be tight in hot conditions. So therefore, if we measure a die, we should give to the outside 0.02 millimeters up to 600th more to compensate once the die gets hot. And I think this is the biggest challenge for every die maker. It does need some experience. The die maker has to work well together with the die caster. And of course, the latest simulation system sometimes are able to show where we would have a higher expansion of inserts or of the whole die because of temperature. But still at the very end, we need to imagine a little bit something which gets hot, extends, and we have to take this into consideration once the die is made to be very successful for vacuum pressure die casting. Then another big point is always the plunger and the shot sleeve. Shot sleeve, even without vacuum, the better the shot sleeve and better the piston, the better the castings in general. In vacuum die casting, even more important. So for standard die casting parts, maybe even with the help of vacuum, we are able to make good castings also with standard pistons. The problem is we probably have to exchange them every 3,000–4,000 shots. If we have a ring piston, if it works well with the application, with the shot sleeve, the ring piston works up to 10,000 shots before changing a ring. So therefore, for a longer time, we are having a tight system for using the vacuum. The oxidation is a very big critical area because, like, if the piston is not tight, we have more oxygen turnover, a higher oxygen turnover inside the die, inside the shot sleeve, and this most of the time is very bad for the quality of the casting. Another problem is if there is more air from the shot sleeve getting through the die, through the whole application. The problem is the airflow in the runner. It has the tendency basically to suck metal. It doesn't really suck metal, but let's say the velocity and the volume of air is higher. Therefore, it has a higher influence on the surface of the metal, which goes towards the cavity. And the die caster was saying, oh, the vacuum was sucking the metal. If we have an absolute tight system, it's impossible to suck metal. The metal will remain because metal it has aluminum in liquid conditions is 2.55 kilogram per square decimeter. So it is not possible that a really vacuum is sucking. But if there is too much air, it will have an influence of how the metal gets towards the gate. And of course, also the piston is moving the metal not in a very smooth way. Often inside there is a little bit of movement, or sometimes even strong movement. If we have all the die cast machines, if the plunger comes out of the zero position, quite nervous, it gives a little kick. Of course, it gives a kick to the surface of the metal, and then we do have even more possibility to suck some air. So what is the result? We can see some orange skin, we can see flow marks. In worst case, we can even see that the cavity didn't fill well in some areas. because some of the metal which has been sucked, it's getting semi-solid and it doesn't fill in some parts of the mold, the cavity that well. Therefore, also some years ago, I think now it's already almost 15 years ago, 14 years ago, we started adapting a regulation system to the vacuum system. So the target is at the very beginning, when the metal gets into the runner system, instead of having a full power sucking, we are regulating the airflow. So instead of like it will make so we can regulate the airflow inside the die in order to have an optimum let's say an optimum alloy flow towards the gate. So this looks in the modern machine, it looks like this. We have even like it's called throttle valves, and we can say in the initial position, the throttle valve may be only 2% open. And then we can say with the time of how much opening we have on the valve, and then we can create vacuum curves like this. So at the very beginning, this, for example, when the vacuum starts at maybe 160 millimeters, up to maybe 250 millimeters in the first 0.6 seconds, we have a reduced airflow. And once the metal really is in the runner, we accelerate the airflow. And when we are filling the part in this area, we still have a very good vacuum level. And therefore, you get a better quality casting because we were able to fill the cavity with the plunger movement. Like as we heard before, like the Bühler machine, Freck, and either on Detail Press, they have like a programmed shot, and you can put in some acceleration in the first phase. So that means the characteristics you gave to the metal flow through the first phase velocities, acceleration of first phase velocities, we are able to regulate the vacuum exactly the way that the metal flow more or less gets close to perfect in the first phase. Of course, we cannot see inside the die, so this also is kind of an exercise. You have to exercise with which parameters we are getting the best results. So the next slide is about the quality of the vacuum curve. So in advanced systems, we are trying also to monitor the curve, as we have seen here, that we are able to create a curve which can be restored in the machine, and then we can compare through 100 shots if we are always with the same curve. And how to create a vacuum. If we want to get to 100 millibar, maybe 50 millibar, maybe 30 millibar, we also need to have a certain size of tank. And the bigger the tank, the higher the capacity we have with the vacuum. That means the quality of the casting can depend on the tank. At the same time, also, we have a big tank. Of course, we can suck a lot of air, but we can suck a lot of wrong air. That means it's possible to get air from the sides of the cavities. At the same time, it's possible also that we have quite fast first shot velocities. Therefore, the time for the vacuum is quite limited, and maybe we are not able to get all the air out. So a good vacuum curve does not always mean that all of the air has been coming out of the cavity. So therefore, we are also using, it's called a measurement of volume, of air volume, which gets into the tank. So here we can see basically the operation, which we have the calculation of how much liter we would expect. And then we have the limits. And here, that's the reality of how much liters we actually get. What was the difference? And here, the basics of like how it worked. Like what was the atmospheric pressure? What is the tank pressure at the start? And what is the tank pressure at the stop, at the end of the filling? And to put everything right, or let's say to know everything, we have like it's called a window where we can put all the different datas in. So like we need to know the diameter of the vacuum hoses, like the length of the vacuum hoses, the temperature factor. Diverse means how many different filters we have built in. If you have 2 channels, you may have 4 filters, one on the vacuum unit and one on the die side for each channel. So there are 4 filters, which gives maybe 2 liters of air. What is the size of the tank? How many liters we really have inside the cavity? And with this, you can say, well, theoretically, if we get out 99% of air, that would be 5.11 liters. 5.11 liter. Then we can put in the tolerance, which we can see here. So if we want to make it sensitive, yes, we put plus minus 10%, or we can put it to plus minus 20, 25%. If one wants to go even further, in big mold applications, we may use 3, 4 vacuum valves or chill blocks. So then we are able to measure on each channel with a special sensor of how much air has been removed by one channel. So each one gives a curve, and it will tell how many liters of air have been flowing through there during the application of vacuum. Then also here we can monitor of like what was too much and what was missing. Again, this is something we have to make shots before we can actually evaluate how much air per channel is a good result. So that means we need to experience first to start up the system and to see how much air theoretically we have to get. Then we can see how much air through one channel gets, and afterwards we can qualify which curve was a good curve or which one was a bad curve. Okay, so next slide. It was vacuum tank recommendations, which I told you before. We always have the question, how much vacuum we should get inside the cavity, what should be the vacuum curve, and how much we should tend. So there are many different approaches, and also it depends on how much money we want to spend and how much security we want to put in. So FONDAREX, we are recommending to start, if we have just some standard applications, we start whatever we have to get out of the mold, we have to get 50 times more into the vacuum tank. So here I put your table, very basic. We may start with 1 to 35. Up to the structural or high-end parts is maybe 1 to 100. And in most applications, we are somewhere between 1 to 50, 1 to 75. So we come back to that. It looks like this. What do we need to take out of the mold is what we have in the shot sleeve and inside the die. That means the cavity. Then we need to take out the filters, which are here, and for example, here on the vacuum unit, and what is inside the hose. That's what we have seen before. If we have 2 channels, each vacuum, not each vacuum unit, but some vacuum units have 1 channel, some have 2. Now on the latest stage, we are going up to 6 channels on very big molds, on a 5,700 ton machine or 6,000 ton machine, we maybe need some more channels. So all this air somewhere has to be moved into the vacuum tank. And everything which is above the vacuum tank, whatever has to be moved into the tank, that's like the factor 1, which we have here. So if we have a calculation, in this case, for example, 5 liters, which is a rather small machine. So we go back to the table. So if we have 5 liters to, for example, 50, and that will be a vacuum tank of minimum 250 liters. So a clever guy maybe gets 300 liters at least, because we want to have some safety as well. And now, of course, if a vacuum unit on wheels, as we can see here, as you can see here, we can use on a 500-ton machine, but at the same time, we maybe can also go to the 750-ton machine. So you may buy directly a 500-liter tank, and you know that the vacuum unit can be good for 3-4 different machines in the die-cast shop. On bigger machines, usually we use the tank directly on the unit, on the die-cast machine, and it will be fixed, installed there. We just maybe put some 20% more security in. If you know that we have to produce a structural part, for example, we know that we have to take out 11 liters, and we won't put 20% security, so you count on 13 and some liters which you have to take out, and with the factor of 100, that means we should supposed to have a tank between 1,200 and 1,500 liters to be perfect. But if we do everything right, probably in this case a 1,000 liters still will do a good job. So this is something we have to evaluate. It doesn't have to be exactly on the liter. The good vacuum die-cast parts, they more come from how we are working with the vacuum and how good is the quality of the molds and what kind of parameters we are putting. But of course, once somebody invests, we have to invest into the right material, and we have to know ahead of what we want and how we want to work. So this is like, as I say, with structural castings, these are always a little bit special, and it's good to have some security in it. So also in structural casting, most of the time we are using kind of like Silafont and some other alloys which are similar to that. They are high ductile. And of course, let's say 50 to 70% are heat treated. So all of those alloys, they benefit in a high percentage on the vacuum. They are made to be high ductile, and that they can fulfill their characteristics. Vacuum will do a very big job with those alloys we can reach best possible castings, which are having up to a yield strength of 290 megapascal after a T6 heat treatment. Of course, today not everybody does have the equipment for T6 heat treatments. There are some other alloys available, and even a Silafont also with the standard treatment, we can get already up to more than 200 MPa for getting good castings, and which can be called structural castings. So the main thing is to reduce the oxygen and the hydrogen during the filling of the parts. So therefore, also in structural casting, a lot of people talk about, we should have vacuum levels of maybe 50 millibars, maybe 30 millibars. Therefore, also inside the vacuum tank, the pressure may be 15 or maybe even 10 millibar. So that means also the vacuum pump has to be a little bit larger to really guarantee very low values in the tank. But the 30 millibars is not always the target. We have made many, many good castings with 100, 120 millibar. Why? Because sometimes, or in most cases, it's more important to have the right characteristics and right parameters, then the best vacuum level. The best vacuum level costs the die caster a lot of money. You have to seal everything perfect. You have to have big tanks. Everything is slightly oversized. The target is just to get basically the air removed from the advancing alloy. If we can do that, we don't need 30 millibars. We can do it with 100. Or I have done better structural casting parts with 100 millibar than in some cases with 30 millibar, because 30 millibar also has much higher side effects. So we have to concentrate on the whole lower concept and on the parameters, and not only on the lowest possible vacuum result. On the other hand, if somebody is investing into a new cell, which is designed for structural part castings, of course, we have to buy the equipment, which can guarantee 30 millibar if ever we need it. Sometimes we need it. So it's not possible to get a perfect part without getting very low. But in most cases, we already get good parts with 100. So this is just like to evaluate a little bit of what we should buy. We are not buying it just because we need all over the place 30 millibar, but we should have the possibility to get 30 millibar. So the square section of chill blocks, of vacuum valves, channels, and so on, they also have to be according to the application. So if I have a structural part which has 1000 millibar, 1000 millimeter square section on the gate, we should have at least 25 to 30% of it on the venting system as well. So that means maybe 300 millibar venting, and therefore also to guarantee, if we measure good vacuum, that really the air comes out of the cavity. So what do we have? The ring piston again is a must, and one of the question is always, do we need a seal? And then of course the seal will always help. It's not always necessary because it depends how the mold is built. But once we build the right mold with enough space, a seal can always help. So we can see here, I have made 2 or 3 different examples. Unfortunately, I'm not able to show all of them. But if a seal goes all around the cavity, far away from where the parting line is, it can make sense why the metal doesn't reach to the seal. Even better is to get a second level. If we have the level, or like here also where the vacuum valve is, even if it flashes sometime, that the metal is not getting directly on the seal. So therefore also the molds are getting bigger, and you have to have the space to put the seal into the mold. There are many different manufacturers of seals. We are working with a German company. I think they're called Emmenegger, but there are many Japanese. Well, there are many different seals around. Depending on the mold, depending on how hot the mold gets, where the seal gets, it has to stand at least 150, 160 degrees. But looking at a mold like this here, like where the vacuum valve is placed, probably here the mold base is only 90, maybe maximum 100 degrees. So that means already a seal of 120 degrees security could do the job in this case as well. The groove can be quite easy to make some radius so the seal doesn't damage, and basically the seal itself, it holds into the groove, which is about 6 millimeters deep. So here I say in some cases maybe the seal should stand up to 180 degrees. The profile is 1865, which we use most. The DIN norm 19,660. That's from Emmenegger. So
John,
anyway,
I think just to interrupt you, I think we are running out of time. It will be really great if you can just wrap it up.
Yeah.
Yeah.
I know my time is almost over, so this is why I'm already at the risk.
Thank you. Thank you.
So anyway, yeah, to make it short, we at FONDAREX recommending in the market to get the equipment which is depending on your application or on the die-cast machine, depending of what you have to cast, and to not focus only on the very best vacuum result, also to focus basically on your characteristics. So that means to not panic if we get only 250 degrees, if I 250 millibars. If I make 250 millibars and I have a perfect casting, I don't need to concentrate on 100 millibar or below. And of course, yeah, we have a lot of experience with many different castings. And if somebody is interested to go a little bit further to get better vacuum or to do something on the application, we can offer over 75 years. Next year, FONDAREX will be 75 years old, and therefore, of course, we can bring you a lot of experience into your die-cast shop. So then I say thank you very much for having us, having me to ALUCAST. I wish you a good second day. And also FONDAREX is wishing you success and happiness and all the best for the new year. Thank you very much.
Thank you, Johan, so much for such a wonderful presentation. I think, there were questions in between, but I wanted to be going because you were answering those kind of questions, and you touched very important aspects of vacuum die casting. A lot of basic things which you touched was really very relevant to the questions which were being asked in the chat. But nevertheless, I would want to put those questions before you so that those questions could be answered. We have in total 5 questions from Mr. Sandeep, and if you can jot it down, I think probably you can answer one by one. So the first question is, how does sealing can be controlled with vacuum? That's the first question. And you want me to have one by one, or you want to have all of them?
Well, you give me one by one. I think it's better. Like as we're sealing is not an absolute must. If we have a precise die, you can make good castings without sealing. If we have a new project and we know it's going to be a high quality project, of course, it's good to plan on the sealing. And the sealing mainly will guarantee you for a longer time a tight die, So because once you have made 80,000 shots, sometimes you had some flash, some deformation, whatever, and the sealing is there to be for a longer time vacuum tight. I don't know if that answers my question. Otherwise, I mean, yeah, I don't know what else to say about the sealing, So it's like if it's getting already more difficult to put the sealing. I have seen seals behind sliding cores, but then there we have to be aware that maybe every 5,000 to 10,000 shots you have to control them, exchange them. It's getting a bit more difficult, yeah.
Yeah, that's exactly the one of the questions which was raised by Mr. Vijay Kumar Yadav is how we can improve sealing and slide cores area of dies for best vacuum performance. The question is in line with what you're saying.
I mean, let's say it goes back to the die maker, to the mold maker. He has to work as precise as possible. Sometimes maybe you have to cut the seals and you have to put maybe one seal this length on this side, then one seal this way. So that means we can do the edges and so on. But it's not like, I don't know, there are not that many possibilities to make something really better. It's just like how precise the die maker puts in the groove and then the seal has to put nicely into the groove. And I think behind the sliding core, it doesn't take that much, to stand out, maybe 0.3 millimeters, and there's always a little bit under pressure. That's all. I don't think we can do that much more. I even have seen very big dies. They had actually two seals. There was an inner seal and the outer seal, But at the very end, I don't know. I cannot say like how much better it was. Yeah. And you see, you can have the best seals all over the place. If the plunger isn't well enough, you still have a weak point, So
They are coming in, yeah.
Yeah, so we can seal the die as much as we want. If the plunger doesn't follow, I think we spend a lot of money for sealing the die, but we still don't get the final result. Yeah, so
absolutely.
To put in the seal, yes, it makes sense, especially if we have the space. If we have to go through sliding cores, you really have to see with the mold makers how to put the groove in, and if is it better to put one seal and to put it around, or to cut it in three and then one seal on this side, on the bottom side, on the other side. It's something you really have to see with the mold maker on the angle and how to put it in. And afterwards, I think the most important is like to control if the seal is always there and if it's on good quality once you are in process.
Yeah, so wonderful. There's one interesting question the question is there any setup to check how much vacuum is created in the dies?
That's also a very good question. And well, maybe to go into details, it would take more than just answering a question like this, because it could be a whole procedure. I make that procedure very short because we can do dry tests, which me personally, as a practical guy, don't like it so much. So the best is always to use a practical test. That means you use liquid metal. With the liquid metal, the piston does also have production temperature. And instead of making a full shot like this, you just slow down your shot. You make the first phase long, and maybe stop the piston when it gets into the filling phase. So when the first phase usually is maybe let's say 2 seconds, you make it to 4 seconds. And then you can see actually how much vacuum theoretically you can get into a die. Because one have to know also the air is getting hot. The air does get different characteristics once you pour the metal. We have maybe an average air temperature of 300 degrees with liquid metal. If you do not put liquid metal, you have much more air volume, which is colder, and you will never get the same result than you will get into the praxis. And therefore, yes, as I say, afterwards we could discuss like the whole procedure, exactly how to do. But the more you want to be close to the praxis, you always have to do the vacuum test with liquid metal, and very important also with the hot die. Maybe you make already 10-20 shots before you do the test of like what your mold really gives in the vacuum stage, because I want to have a tight mold in production temperature.
Correct. So the last question, because we're running still, we've actually crossed a lot of time, but one last question I would want you to answer quickly is, can vacuum help in avoiding shrinkage?
In the what? In the welding?
In avoiding shrinkage. No. The question is, can vacuum help in avoiding shrinkage?
No. Well, no. In everything all around shrinkage, if you go just directly like this, no, vacuum doesn't help. But if we overlook the whole application, and let's say we try to make everything a little bit better, and you may be able with optimum first phase and then optimum filling process, you may be able that you may bring 0.5% more volume into the mold before the solidification phase starts, and therefore maybe you can reduce a little bit of shrinkage. But sometimes can be also opposite. It can be also opposite. If we have an extreme part, which is very thick, just in one section, and you're maybe not able to put the squeeze pin there, or you're not able to really cool it, since we use the vacuum and you have a lower the part, you have a better metal structure, and somehow the part has to shrink somewhere, and it will shrink on the thick section. It could be in worst case under vacuum that the one shrinkage is getting even larger under vacuum because all the rest is perfect. So and therefore also we may get to that point, not always the best vacuum level is giving the best result. Sometimes you just have to take out a little bit of air to get an overall part, and then we have to start handling that shrinkage. But if it comes up to only shrinkage, you just have to keep in mind it's not the vacuum which is solving your shrinkage problem. If you are very clever and if you go very far, you may be able to make it a little bit better. If it's a very thick section or a very special part, it could be also worse under vacuum. And therefore, it's a very interesting question, but I think it's not possible to answer it in 1 minute or so.
Yeah. Oh, absolutely. And we have to wrap up this now. But you really made some interesting observations about the level of vacuum, and not necessarily every time we need to be going back to 50 or 30 millibars. Maybe sometimes 100 millibars gives you better results. Then you really made some very good basic observations and very interesting.
Yeah,
thank you so much, John, for being there and giving this.
Maybe one more point just to say also the vacuum level. I had, I think 4 years ago, also at ALUCAST once a presentation of like where to measure the vacuum. Because the whole industry, there is no regulation of where do you measure the vacuum. Absolutely. Because I mean, it would be, if possible, I would love to measure the vacuum completely inside the die. Yeah. If you use a mechanical vacuum valve, you can say you are very close to the inside of the die and you have a quite precise value of, or like a vacuum curve of what really happened. But often we use chill blocks. With the chill block, you measure somewhere above the mold, and some guys measure 80
at some distance.
But maybe inside the die you had 200. And so it's very relative also of like exactly of what we measure.
Great. Thank you so much, John, for this wonderful session. And it was wonderful to end the day with you. And thank you so much for being there. And I would, ask Samida to take over and conclude the session, conclude the day.
Okay, you are most welcome. It was a pleasure for me to be with ALUCAST, and I wish you all a good evening and then a special good second day tomorrow.
Yeah, thank you so much. Thank you.
Okay, bye.
Samida, are you there?
Absolutely.
Bye. Thank you.
Thank you all. It was a wonderful day with such fantastic presentations and question answers. I think it kept us all really going. And today, we would like to make one announcement. Tomorrow, you will use the same registration link, what you received today or day before or earlier, and you will be entering the conference. And we look forward to an equally exciting day tomorrow. So with this, I think it's a nice evening, and we say goodbye to each other and see you all tomorrow.
Thank you.
Thank you.
Thank you.